This is a design day presentation for Team 4, the wind tunnel lift drag balance.
Introduction. Our project is a redesign of one of the labs in the TFES course, which involves finding the lift and drag forces on a symmetric airfoil. There's two main issues with the lab right now. The first being excessive noise in the data obtained, as seen on the figure to the right. This is caused because of only having one single pivot point, along with resonant excitation of the magnetic coil in the LVDT sensor, which records the forces. The second problem with the lab is the changing of the angle of attack. This has to be done by hand with a long Allen key while referencing a protractor, as you can see on the figure on the bottom. Customer requirements and metrics. Our metrics and milestones are shown on the table to the right. These milestones came from our customer requirements. As you can see, 4 out of our 7 milestones were accomplished during the duration of our project. We were able to achieve less than 2% fluctuations from the mean in our current airfoil and sensor design. We were also able to obtain motor control of the angle of attack of the airfoil, which is done through a servo motor. On top of this, we were able to complete a MATLAB GUI, which allows our entire lab to be run through one program. We were not able to achieve a load cell selection, a finalized airfoil, and a final working product. During our testing period, we ran into issues that were unexpected and complex, and unfortunately, due to time constraints, we were not able to achieve these milestones. And these uncompleted milestones will be talked about later in the presentation.
Our final design, shown on the right, uses 2 mounting points to reduce the overall vibration of the system. It also uses a servo motor to automate changing the airfoil's angle of attack. The airfoil is a carbon nylon 3D print that we finished with an enamel coating and several sanding iterations to improve the surface finish. To measure lift and drag, we built a load cell using strain gauges, which are more sensitive and reduce the vibration further. Motor selection. Looking at our customer requirements, we see that our design must electronically change the angle of attack with a push-button control and must decrease the vibration and noise from the current lab design. We then selected 2 motors that meet these requirements, a stepper motor and a servo motor. Our metrics of success for deciding between the two were that the angle change must be within half a degree of the desired angle, and the fluctuations of output data must be within 2% of the average value recorded. After testing both motors, we see that they both meet both metrics of success. For angle change accuracy, the stepper motor had an error of 0.156 degrees, and the servo motor had an error of 0.179 degrees. Next, the force data collected for both motors followed a normal distribution, which allowed us to use the empirical rule to quantify fluctuations. We found that the data was within 0.586% of the average for the servo and within 3.763% of the average for the stepper motor, allowing us to confidently select the servo motor for the final design.
For MATLAB GUI, our customer's requirements were to have the angle of attack be adjustable by an electronic push-button system, and the program would be simple enough to be practical for use in an undergraduate lab. This led to our metric of success being that the angle of attack change and data collection can both be done by using only one simple program. The results of this can be seen on the right. By using the start button, the data collection will begin, it will display on the graphs, and then be exported as an easy-to-use file for students to use in their lab reports. The buttons on the lower left can be used to increment the angle of attack of the airfoil and reset it back to 0, while the current angle is being displayed to the GUI.
For the airfoil surface finish, our customer requirement was that the new airfoil must be as smooth as possible to reduce turbulence and skin friction. The design metrics were to 3D print the airfoil and produce a roughness average less than 0.056 micrometers, which is the surface roughness of the current TFES lab airfoil, and also remain within the required price and time constraint. The result that we achieved was by applying an enamel finish with a series of sanding passes up to 400 grit sandpaper, and we used a profilometer to measure the surface roughness and found it was 0.75 micrometers. For the sensor selection, we are deciding between the current LVDT sensor and our designed sensor that implemented strain gauges. The customer requirement for this was to decrease vibration and noise from the current design, and we needed to closely match the published data for the lift and drag values that we collected. The design metrics for this were to compare and proceed with the sensor that produced the least noise in the data from angles measuring 0 to 16 degrees, and we were planning to get between plus and minus 2% error, and we needed less than 5% average percent error from published data. The result from this was that the new strain gauge sensor does have a lower coefficient of variation in the raw output, and that's 1.25% for the old LVDT sensor as compared to 0.58% for the new sensor. After our initial calibration, the results did not follow published data well enough, so we may need to continue calibrating, or we would just go back to the currently used LVDT sensor that met our customer requirements.
So wrapping up what we weren't able to achieve, first off, the surface finish. It's not smoother than the current lab airfoil. The opinion of our advisor, who has a background in fluid mechanics, is that this won't make a noticeable difference in the lift and drag force data. On the other hand, not meeting the customer requirement of lift and drag data closely matching published data, looking back, we probably should have added a metric, which is shown in red text on the table, not currently there before, of having our data less than 5% average error away from the published data. And so the load cell selection was made about a month ago, and due to the time constraint of only having a month left, even though our strain gauge cell still has the potential of working, we should have just modified the old cell, the old LVDT cell, and modified that to that design because that cell has shown that it more closely matches published data.
Moving forward with this project will require further refinement of the calibration procedure used for our lift drag strain gauge sensors. Previously, we calibrated the lift and drag strain gauges independent of one another. Using this calibration method provided consistent readings. However, we found that our data was not accurate compared to the published data. While troubleshooting the discrepancy in data, we decided to perform a finite analysis on our sensor design. We found that the lift and drag strain gauges were not independent of one another as previously thought. To test this, we applied a load to the lift sensor and recorded the change in both the lift and drag sensors. We found that the drag sensor increased roughly 1/3 of the lift sensor increase and vice versa. We believe the calibration can be improved by simultaneously gathering data from both sensors while applying a known load to a single axis. Doing this across a wide range of loads would provide a data set that would allow us to create a curve fit function with a force output for that axis dependent upon the lift and drag sensor inputs. Unfortunately, we discovered the sensor's dependency late into the design and have not tested this theory. If this approach proves false, then the new fixture for the LDVT sensor we previously made may need to be implemented.